Greetings everyone. Today I'll be discussing about TomoCam, an accelerated implementation of model-based iterative reconstruction, which is powered by a GPU and which leverages the non-uniform fast Fourier transforms approach. Additionally, we'll explore an exciting prospect of detecting brain injuries through Fourier analysis of sinograms. So let's begin our presentation. Let's start with a concise overview of tomography. So what is tomography? Tomography is a method used to visualize the internal structures of objects without the need for physical dissection. It entails acquiring multiple 2D images or slices from various angles around the object and then reconstructing these slices into a 3D representation of the internal structure. The key to this detailed view is that tomography doesn't just rely on the single X-ray image. Instead, multiple images are taken from different angles. These images are then fed into a computer where mathematical algorithms combine them to produce a three-dimensional representation that reveals an incredibly detailed view of the object's internal structure. However, in many cases, the number of images that can be collected is very limited. For example, collecting sufficient images from a rapidly evolving sample can be very challenging before it changes shape. In cases where only limited range of projection angles are available, direct methods may struggle to produce accurate reconstructions. In summary, while direct approximation methods like FBP are valuable for the simplicity and speed, their limitations become apparent in complex experimental scenarios. And one solution to this is model-based additive reconstruction, MBIR. In medical imaging, particularly in computed tomography, MBIR refers to a reconstruction technique. It involves using mathematical models and iterative algorithms to reconstruct high-quality images from raw data obtained during imaging. Starting with an initial guess, a simulated model of the sample is gradually improved to make it simultaneously match the X-ray measurements collected during the experiment and then satisfy sample assumptions. And then we continue this iteration till the model converges. However, the adoption of MBIR has been limited due to the significant computational resources required by the conventional implementations. And now coming to TomoCam. TomoCam is a GPU-accelerated implementation of MBIR that is based on the non-uniform fast Fourier transforms approach. The TomoCam overcomes this computational cost limitations by reformulating the fundamental operators in MBIR in terms of samples Fourier coefficients, which describe the fundamental frequencies of the sample's density, which is similar to the individual notes that make up a piece of music. And also it leverages the computational power of GPUs. Before going into the operational principles of TomoCam, let's briefly explore the radon transform on the Fourier slice theorem. The radon transform is the integral transform that takes a function f of xy defined on the plane to a function rf defined on the space of lines in the plane whose value at a particular line is equal to the line integral of the function over that line. The Fourier slice theorem or the central slice theorem relates the one-dimensional Fourier transform of a projection with the two-dimensional Fourier transform of the region of the image from which the projection was obtained. By central slice theorem, the Fourier transform of RF in the direction of n cap is equivalent to the slice of the Fourier transform of f along n cap. And this equation is shown below. And now coming to the NUFFT approach. When sufficient projections are available on a discrete uniform grid, inverting the radon transform involves computing Fourier coefficients along radial lines using a one-dimensional fast Fourier transform. This is followed by a two-dimensional inverse Fourier transforms from a non-uniform polar grid onto a Cartesian grid. This process can be represented as a summation, which is shown below, where Cj is a Fourier coefficient at Kj, n represents the number of discrete points representing the sample density f on a uniform Cartesian grid, and m represents the number of polar grid points representing the projection data. As shown below, the direct computation of this equation is computationally very expensive, and we come with an alternative approach. The use of non-uniform fast Fourier transform as an efficient method for computing the inverse radon transform in tomographic images is shown below. So on all this seemingly complex and intimidating process can be broken down into three steps which are understandable. The first one is computing Fourier coefficients on a polar grid using a sequence of one-dimensional FFTs along radial lines. The second one is convolving the computed coefficients with a compactly supported spreading kernel. Evaluating this convolution on a uniform grid follows this. And the third step is performing an inverse Fourier transformation on the convolution values and then dividing them by the Fourier transform of the kernel. So this is the basic process of the NUFFT approach. And now we'll see the role of kernel in the NUFFT process. The kernel is introduced to address the non-uniformity of the sample data. It acts as a weighting function that adjusts the contribution of each data point based on its position. Now think of the kernel as a smoothing function that spreads the influence of each data point to its neighboring points. This is especially very important when the data points are irregularly distributed. A wider kernel allows for a more accurate representation, but may also increase the computational cost. Also, the FFT operation is highly parallelizable, making it well suited for modern computing architectures, including GPUs. This parallelization capability allows multiple FFT computations to be performed simultaneously, which further enhances the computational efficiency. The reformulation of MBIR operators in terms of Fourier coefficients and the use of FFT result in a reduction in the overall computational complexity, which makes it more feasible to perform iterative reconstructions on large and complex data sets. Next, my friend will delve into the intriguing topic of Fourier analysis of sinograms for detecting brain injuries.
Hello, I'm Purnachandra Giridhar. And as my teammate Pranav explained you about TomoCam, that was our motivation to take this project. And since TomoCam used Fourier transform to make complex computations simpler, we thought that Fourier transforms would make it easier to detect injuries from brain CT scans. So that was the motivation of our project. And yeah, so we already had a data set provided, and the data set was of sinograms, and each sample had a shape of 360 into 362 into 363, where 360 was the angle, 362 was the length of the projection, and 3 was the window size. This 3 represented that how much intensity was absorbed by different parts of the brain. And we didn't use much of this channel in our project. And yeah, since we already had sinograms, which is nothing but radon transform, for finding Fourier transform, we just had to do Fourier slice theorem. And it's clearly shown in the figure that we take radon transform at a particular angle, then you do 1D and FFT, and then you get a projected line in Fourier space. So we use this Fourier space as our feature. For that, we also had a different text file, which had all the training data, testing data, and validation data. It had both image name, that is nothing but the sinogram's name, and this ground truth, which indicated whether the brain was healthy or unhealthy. These are some of the images from implementation. These are scan. This is the magnitude of the Fourier transform, and this is the phase of the Fourier transform. This is a sinogram of the scan, this is the training data set which we are having. So since we are having sinogram, we had to use Fourier slice theorem to get the original training set. This is our new training data, which is nothing but the Fourier space. This is again a scan of the brain. Architectures we implemented. Since we only had sinograms, and again, the text file was in a different folder, the sinograms were in a different folder, we had to do a custom data loader, where we take names from the text file and then import the sinogram and then again attach its ground truth to it, and also find the magnitude of the Fourier transform. So we couldn't use a normal data loader which PyTorch gave, so we had to code it ourselves. And we also implemented 3 different types of networks, 2 based on convolution neural networks, and the other one is based on efficient net. And when we implemented it, we saw that the CNN networks gave better results than efficient net. Efficient net didn't give promising results, so we didn't further continue on it. And yeah, since it was our first time training this model, we had to do more hyperparameter tuning, and also we like trained it with different learning rates, trained it with different data sizes. Yeah, so we did different things to get better results. Yeah, this is our custom data set. As you can see, we are taking only the magnitude of the FFT, that is abs of FFT. This is our first architecture, first CNN based architecture. And this is having 3 convolution layers followed by pooling, and each convolution layer is having a ReLU activation function. After that, we reshape the output feature map of the 3rd convolution layer and pass it through a fully connected neural network which had 2 hidden layers, as you can see in the picture here. And as we trained it for 15 epochs, we could see that our training loss significantly decreased from 0.571 on the first epoch to 0.02 on the 15th epoch. And train accuracy increased from 0.71 on the first epoch to 0.99 on the 15th epoch. But our validation accuracy didn't change much, but our validation loss increased. We could say that this was prone to overfitting, and we still tried increasing the data set size so that the model could train well, but that only increased the computation time from 25 minutes per epoch to 3-4 hours per epoch. So we tried changing, so we came up with a different architecture that I'll show you in the next slide. With the testing data, we got an accuracy of 71%. I would say this was not very good, but it showed some promising results. This is our second architecture. Since the first architecture was prone to overfitting, we added new dropout layers, which could help us from like resolving this overfitting. Similarly, this was also prone to overfitting, but gave us better results. The test loss, as you can see, became more than 1/3 the previous, and the accuracy also increased by 2%. So this was promising for us. Yeah, and these are the flaws of the second architecture. It is prone to overfitting, but it gave us better results. Future research prospects. Since we had limited amount of time and we had to understand everything from TomoCam and implement the new code and understand how our data set is and all, it took us time, and we could not completely work on everything what we thought. So some of the ideas we had and we can work on it on the future is, first thing is implementing both magnitude and phase. As you know, magnitude only contains not everything, not all the information, and phase also contributes to the information. So we can add an extra channel called phase channel, and then we can try to put it in the architecture and see how it is coming. The second thing is, since radon transform or sinograms are nothing but slices at every angle, we can use RNNs, which work better with slices and continuous data. And also, since both our models were overfitting, we can also increase the complexity of the model so that it doesn't overfit. And so, yeah, combining results of Fourier analysis with conventional approach warrants investigation to ascertain whether enhanced performance and outcomes can be achieved. Conclusion: the results achieved, while not be groundbreaking, are nonetheless promising and encouraging. As you can see, our accuracy increased from 71% to 73% just with adding 2 dropout layers. We can also increase the complexity and get better accuracy. And since we are using only Fourier transforms, this will help the medical field very much, because computation and just detecting the brain injury doesn't take time. It takes less than 5-10 minutes. But what methods we are using now takes more than half an hour. So this would be a very good thing in saving people's lives. Yeah, in conclusion, this area holds significant promise of further research and stands to offer substantial benefits to the field for medical imaging. Thank you and have a good day.